emulation-based full chip level low power valid at a pre-silicon stage. Instruction: IP and block level power estimation low power feature verification has become a must for mobile AP development. Additionally, it's become possible to analyze power consumption based on more realistic scenarios such as running as real applications in OS level, so the power consumption is optimized in the full chip level during the RTL design stage. This typically requires a full chip environment as opposed to an IP or block level environment to run realistic or benchmark scenarios. Thus, this is a full chip level environment enables more realistic scenarios at the RTL design stage. Power validation for hardware-based power optimization features can be achieved before silicon. Also, long scenarios of several milliseconds to a minute can be profiled to optimize the power consumption at full chip level. This paper presents a low power feature validation flow and the result at the free silicon stages. Introduction: IP level and power, a block level power feature verification using RTL and gate level simulation is a necessity for a mobile AP development. However, focusing at the IP and block level doesn't cover a system level power feature verification. At the full chip level, the clock management unit and power management unit does not control the overall system power management. Power feature verification can be accurate after full chip integration with those system IP. However, RTL and gate level simulations are slow, so they cannot verify various realistic scenarios based on firmware or OS level in full chip. Thus, if the full chip level verification environment enables more realistic scenarios RTL design stage, power validation for hardware-based power optimization features can be achieved before silicon arrives. Furthermore, long scenarios of several milliseconds to minutes can be profiled to optimize power consumption in a full chip level. This paper describes the validation flow for low power features using realistic scenarios with a full chip level RTL. The RTL optimization is switch validation using the low power features further discussed. The results show a good correlation between the power estimation at RTL and the actual measurement at the post-silicon stage using the low power features. The rest of this paper is organized as follows. This section is in the introduction, and section 2 is described traditional power validation flow at the pre-silicon stage and the power validation method at the pre-silicon stages, which this paper proposed, and it shows the respective flow chart. In section 3, the techniques to reduce the turnaround time (TAT) in our flow are described. It includes a sampling, a ratio control scheme, and using the power critical signals. In the section 4, we provide the result of applying this flow to our latest mobile AP product and a correlation with the silicon measurement. Lastly, section 5 offers our conclusion of this work. Power validation method. In this section, the traditional power validation flow, which is used to post-silicon, is described. Furthermore, the proposed pre-silicon power validation flow is presented with a comparison to the traditional power validation flow. The traditional power validation flow at post-silicon stage. As a figure 1, The one shows validating low power features and optimization power consumption in the full chip or system level is performed during the post-silicon. However, power analysis at the post-silicon stage can't improve the power power hardware power optimization and can only influence software-based software-based power optimization because the hardware design is already fixed. If bugs are found in the hardware-based low-power features, it's difficult to fix them at the post-silicon stage. Fixes cannot be applied to the current power version, and they should be implemented in the next hardware version. Figure 1. Power features validation flow at the post-silicon stage. 2. Mitigate both software workarounds are used or low power features are disabled completely. Thus, it is possible the product encounter power issues. Product may not meet important power specifications such as a mobile AP battery consumption, which is defined during product pruning. Silicon power is measured at the current power of layer or power sources on the board. Next, the power features are enabled and validated and the power savings are studied. Using this method of the chip factor can affect the validation result, but it is difficult to debug internal hardware modes or the off-chip environment when there is an issue in silicon. The full chip level RTL simulation environment is not secured so that the silicon scenario cannot be reproduced easily. This makes that seamless debugging is not supported at post silicon. Thus, this leads to developing design and verification process at the pre-silicon stage during RTL design period. B. Proposed power validation flow at pre-silicon stage. The proposed flow utilizes an emulation-based full chip RTL environment to shift the low power feature validation and power analysis from the post-silicon stage to the pre-silicon stage. Figure 2 shows the new validation flow based on the pre-silicon stage. This proposed validation is for validating the hardware power feature by using almost same firmware OS validation environment in pre-silicon as is used in silicon in post-silicon. Figure 2 is the power feature validation flow at the pre-silicon stage. First, the power features can be verified with the profile switching activity from the emulation result. For example, when enabling low power feature can any point during normal operation scenarios of the firmware, the low power feature, that is clock gating, can be verified with the switching activity graph. If debugging is required, the emulator can provide the waveform for all signals with full visibility. This enables effective debugging. Furthermore, if the needs to be modified after debugging, the hardware can be modified right away. This is in contrast to the hardware debugging during the post-silicon. The hardware issue debugging during post-silicon is difficult because getting the full visibility in hardware design is limited. Also, it is not easy to modify the hardware design after silicon is released and thus pushes fixes to the next design version. After low power feature verification, a low power calculation tool can estimate the power savings by analyzing the FSDB of SIFE for interesting simulation time period. With this result, the effect from the low power feature can be estimated separately. This enables the software development team to optimize the power at the system level using the the already validated low power features. This is in contrast to the traditional flow where system level power can be optimized only after low power features are validated on real silicon. This can reduce the power post-silicon software development time and impact the overall TAT of a product by shortening the development cycle. A method to reduce TAT. The overall flow for executing a long simulation-based full chip was developed. The first low power profiling methodology for executing long multi-second scenario is deployed. When a realistic scenario is profiled with a full waveform full dump, it takes several days for running emulation and dumping the waveform and profiling switching activities to reduce the TAT for these steps with the guarantee of a good accuracy. A sampling ratio control flow is evaluating proposed. Second, a power estimation methodology is developed to handle long scenarios. The power value is calculated for realistic scenarios with full chip signals. It takes several days for dumping all signals and calculating the power value. To reduce TAT for estimation, it is proposed the power regions of interest are selected from power profiling. The specific signals preferred to power critical signals are used for the power calculation tool as opposed to the full chip level full signal dumping. Yes. Sampling ratio control. Signals are dumped, sampled for all cycles by default on the emulator. If sampling ratio is controlled, the same signal can be dumped only for 10 cycles out of 1,000 cycles. So when a switching activity is profiled using the sampling ratio control, significant reduction of TAT was achieved without losing much accuracy. The figure 3 shows how much correlation can be achieved with these different sampling ratio. The first graph, figure 3, the sampling ratio control is correlation. The first graph depicted the switching activity for full cycle dump by default. The second graph shows a 1 over 32 full signals cycles, and the third graph signals displays switching activity with only 1 over 1 and 56 for full cycle. The whole activity trend shows a high correlation for all three graphs. Thus, sampling ratio can be controlled with the consideration of the accuracy by use case or scenarios. Table 1 shows the reduction of on-disk space and runtime in full chip level during the period of 100 milliseconds. The evacuated design size is around 50 billion gauge. The dump file size is reduced up to 150 times, and emulation runtime is faster by up to 20 times. Profiling is most processing work, and 15 cores of the computing farm are used to generate switching activity information. Profiled file size is reduced by up to 241 times, and post-processing runtime is faster by up to 176 times. When a realistic scenario like OS boot-up or an Android application runs on an emulator, this technique will be very useful to profile power with a short AT-AT. Table 1 is sampling ratio control and reduction resources. The power critical signal flow. The power estimation tool can select the signals which are most critical to calculating power. The number of these power critical signals is normally around 10% of the full signals. So the only power critical signals are used to make FSDB or cipher and are used to calculate power on the power estimation tool. TAT will be decreased increasingly. Figure 4 shows how power critical signals are generated and used in emulation. The flow is almost the same with the using full signals, but two steps are added. Power critical signals generation and FSDB generation only for power critical signals. The power estimation tool can generate power critical signals at the elaboration steps with no additional effort. When low power regions of interest are selected from the power profiling step, an FSDB and SIF can be generated only for regions of interest with power critical signals from power estimation tool. When the power estimation tool uses this FSDB or SIF files to calculate the power value. Figure 4 Power critical signal flow. A power critical signals flow was applied to calculate an average power, and as result were achieved as described in table 2, and the number of signals were reduced by the 92.5% of this reduction directly impacted the FSDB generation power time and power calculation time with the proper average power difference. A power critical signal flow does not affect the emulation run and dumping time or switching activity profiling time. Thus, the result of those steps are the same as using full signal flow. The evaluated design size around 50 billion gates, and the time is around 100 milliseconds, and the region of the interest of 10 milliseconds. This region is generated to the FSDB and is used for calculating the average power. Experimental result. Using the proposed flow, our latest mobile AP was validated at the full chip level with a special care toward low power features such as clock gating schemes at the RTL design stage before silicon. While evaluating low power features, several hardware bugs correlated and firmware versions were fully developed to enable those low power features properly. Table 3 shows the ideal state impact of the system level low power feature. The number is normalized to explain the effect of the low power features. When a low power feature 1 is applied, the low idle power consumption is reduced by 54.2%. When low power feature 1 and low power feature 2 are applied together, the idle power consumption is reduced by 77.8%. Table 3 result of power validation, idle power. The table 4 shows the activity power consumption when lower power features are applied. When low power features 1 and low power feature 2 are applied together, the active power consumption is reduced by 27.2%. The region of the active power consumption is the most heavily operated. The most power production level is less than the reduction of the power assumption. The average TAT without using the sampling ratio and the power critical signal flow the running emulation with the firmware with various power features is about 15 hours. This includes the power calculation only focused on the memory interface and the data bus operation based on full chip level. The FSDB, which is used to calculate the power periods, is 10 milliseconds subset of full chip level runtime to select the interest region from the whole scenario. First, the sampling ratio control scheme was used to profile the whole scenario period of around 5 seconds. Then only a 10-second period was selected to calculate the average power. So the TAT was almost the same with the first result but the total scenario period was expanded by a factor of 500. As Table 4 shows the real silicon when the low power feature are applied to at the OS level with the same scenario. The estimated power values from the RTL design stage are tightly correlate with the result of OS level measurement. But some other samples correlation is various. The OS level power measurement is affected by the various on-chip and off-chip environment effects like board and package. However, the proposed flow only focuses on the chip environment without any off-chip environment, thus not absolute power value suitable for silicon correlation but suitable for evaluating power saving effect of various power features. Table 5, silicon relation. And 5. Conclusion and future work. A full chip level for a low power feature validation and estimation flow at the pre-silicon stage is proposed. Using the proposed flow, we can shift left or perform full chip power estimation and low power features validate from the post-silicon stage to the pre-silicon stage, as significantly improved discovering hardware design issues at the early stage and is expected to reduce SoC project schedules using the emulation-based power analysis solution. This proposed solution is applied to our mobile AP developed based on these experimental results. Furthermore, post-silicon power leaders a scenario are used during the pre-silicon to expand power coverage to the whole chip. This proposed solution is just the beginning stage to cover full chip or system level power estimation as pre-silicon using an emulation environment. Many factors need to be considered to enhance the power analysis at pre-silicon stage. For example, verifying between the power source, that is PMIC, and an SoC is critical. If the PMIC and SoC verification environment can be produced with the power issues related to peak power between the PMIC and SoC can be investigated and solved. However, integration of analog components should be supported on the emulation environment. This is an important area for industry to collaborate on. Dynamic voltage frequency scaling support DVFS support is required to operate the firmware or OS level scenarios is an identical fashion to silicon. The software development team analyzed and optimized power while controlling the DVFS. Currently, frequency scaling is handled partially in an emulation environment, but voltage control and effect to the power analysis are a challenging topic in this area. The TAT reduction enhancement for long scenarios low power analysis flow has been proposed in this work. Software developers typically request a fast environment and large power during the pre-silicon. New solutions are developed to meet a software development teams required for speed. For example, calculation logic for switching activity can be inserted into the emulation hardware, so switching activity can be generated in real time during an emulation run. In terms of TAT, significant enhancement, power profiling, and estimation flow will achieved using this solution. The high-fidelity emulation platform is another promising solution to improve our proposed environment, expand on the configuration, but hybrid emulation speed is faster than the pure emulation environment. Thus, if the emulations can be used to profile and analyze power, the TAT might be shortened significantly. The acknowledgement, references. Okay, thank you for your time, for reading the paper, emulation-based full chip level low power validation as pre-silicon stages. Thank you.